Have you ever encountered this situation? The code looks perfectly correct, but after compiling, it exhibits completely inexplicable strange behavior. Or even worse, with O2 or O3 optimization enabled, the program's behavior changes entirely. Either it outputs bizarre values, suddenly hangs, or code that should obviously execute just disappears. You might think it's a compiler bug, but today I'm here to tell you, it's not a bug. You've triggered C++'s most terrifying, mysterious, and easily overlooked underlying mechanism, undefined behavior. In this video, I'm going to dissect UB completely. After watching this, you'll understand the underlying principles better than 90% of C++ engineers. First, let's break it down. What is undefined behavior? The C++ standard puts it in one sentence, but it hides the harshest rule. When a program exhibits undefined behavior, the standard allows the compiler to do anything. No, that's anything. No boundaries, no constraints. At best, the program crashes or outputs garbage. In moderate cases, the code behaves completely differently across compilers or optimization levels. At worst, it appears to work fine, but suddenly triggers fatal bugs in production. Most bizarrely, the compiler might decide this code's result is meaningless and simply delete it entirely. Let me show you a classic counterexample. For the code on screen, what's the value of y, 3, 4, or 5? You'll never guess. Because there's no sequence point between modifying x and accessing x. Simply put, there's no clear boundary for execution order. This directly triggers UB. Key point here, UB is not the result is uncertain, but the result fundamentally does not exist. The standard has no rules constraining the execution logic of this code. The compiler is free to handle it however it wants. At this point, some might complain, since UB is so problematic, why not just define its behavior clearly? Wouldn't it be better to throw an exception like Python? The answer is simple. C or C++'s core mission is to approach the performance limits of hardware and to compile into efficient CPU instructions. These two goals determine that UB must exist. Imagine if all behaviors were strictly defined. Compilers couldn't freely reorder instructions. They couldn't perform aggressive optimizations, like deleting seemingly useless code. They'd have to check every array access for bounds violations. They'd have to assume pointers might point anywhere. The consequence? C++ would completely lose its identity as a systems-level language. Performance-critical domains like operating system kernels, database engines, game engines, and embedded firmware would become nearly impossible to write. So, the essence of UB is a contract. The programmer promises the compiler, I won't do bad things, and the compiler rewards them with extreme optimization performance. It's precisely because of this contract that compilers can confidently perform key optimizations like constant folding, directly computing constants known at compile time, dead code elimination, removing logic that will never execute, instruction reordering, making CPU execution more efficient, alias analysis, reducing redundant reads-writes by determining if pointers point to the same memory, auto-vectorization, using SIMD instructions to accelerate loops, register allocation optimization, reducing memory access to boost speed, and more. These optimizations are the core reason C++ performance can rival C, Rust, and even assembly. Let's look at a classic example loved by the entire industry for teaching. Look carefully at the code on screen. You're writing to memory outside the array bounds. You might think it's just writing to the wrong place, but from the compiler's perspective, this line of code is saying, this program has already violated the standard. Compile it however you want. Thus, the optimizer might decide the R array won't be used normally afterward and delete all code accessing array. It might even delete the entire function or optimize the program into an infinite loop. One of the most shocking examples comes from Clang. If you write code like this, you might think the logic is fine. But if your program triggers UB elsewhere, for example, an out-of-bounds access in another function, the Clang compiler might generate assembly code like this on screen. Why? The compiler's logic is, since the program already has UB, the semantic correctness of this loop doesn't need to be guaranteed. So, it simply gives up and generates the simplest instructions. At this point, many might think UB is a compiler problem, but its root cause lies in hardware. The underlying rules of the CPU determine that UB must exist. To pursue performance, CPUs have their own set of rules. For example, first, out-of-order execution. Just because you write code to execute A then B doesn't mean the CPU will follow that order. It looks at which instruction can be computed first without causing delays, and runs that one, aiming to utilize hardware resources fully and improve parallel processing efficiency. Second, write buffers. When a CPU writes data to memory, it doesn't write immediately. It first stores it in a temporary cache called a store buffer, waits until a batch is ready or the timing is right, and then flushes it to memory in one go. This reduces the overhead of frequent memory access. Third, branch prediction. The CPU guesses which code will likely execute next. For instance, if an if condition is highly likely true, it pre-executes that code. If the guess is correct later, it uses the result. If wrong, it discards it. This avoids waiting and saves significant time. Fourth, Cache coherence protocols, like MESI. Modern CPUs are multi-core, each with its own cache. To prevent chaos when different cores read-write the same data, the MESI protocol ensures all core caches remain synchronized and consistent. Finally, memory alignment requirements. When a CPU accesses memory, it doesn't read from any arbitrary address. It must align according to certain rules, for example, 4-byte or 8-byte boundaries. If unaligned, some CPUs crash outright. Others run extremely slowly. The design principle of the C++ standard is, don't restrict the CPU's optimization capabilities, and don't force the CPU to pay for erroneous behavior. Thus, any behavior that could violate the CPU's memory model is marked as UB. Common examples include unaligned access, dangling pointers, array bounds violations, modifying const objects, strict aliasing violations, and data races. Among these, data races are the most terrifying UB in concurrent programming. They don't cause clear crashes but lead to ghost bugs. For example, for these two statements on screen, you might think y must be 1, but the CPU might execute read x first, then execute write x equals 1. Cache the write x equals 1 data in the store buffer, fail to flush it to memory promptly, causing other threads reading x to see the old value. This is why the C++ memory model explicitly states data race equals undefined behavior. Once such behavior is defined, CPUs would have to disable out-of-order execution, write buffering, and other optimizations, causing performance to plummet. So, to avoid UB from the ground up, you need to master some techniques. Use tools like UBSAN, ASAN, and Valgrind to dynamically check for various UB conditions. Adhere to strict aliasing rules. Don't let pointers of different types point to each other. Use modern C++ features for memory management to avoid dangling pointers. Use STD's atomic for concurrency to avoid data races. Apply RAI to manage resources and avoid leaks. The core principle is, never assume the behavior of UB. Don't think this UB code worked before, so it's fine now. UB behavior has no pattern. Compiler versions, optimization levels, or even CPU models can change its manifestation. In summary, UBC++ plagic and also its trap. To use it, you must understand it. If you enjoyed this deep dive into underlying logic, remember to follow me. See you next time.